Hey, so now you know everything there is to know about thermodynamics, sort of, and you know a lot about bonds, but you know we never really told you why are some compounds more stable than others, and why do some reactions have a delta H that's positive and one that's negative. I mean, we calculated it all and all that kind of stuff. We never really told you why. So for example, that reaction right there is due to the energy required to break the bonds of this phosphorus sulfur compound on the head of this match, and in return we now produce phosphorus and sulfur oxides, and those have different energies to break those bonds and different energies when those bonds are created. Breaking bonds takes energy, forming bonds releases energy, and now we have a new tool. It's a table of bond energies, and if we use it properly we can then touch off this reaction where we actually, that's not a good idea at all. I need that later. There. So when touching off reactions, it's always good to have a cat squirter handy. Let's go talk about bond energy right now. Well, hi everybody, hi, Mike here. Today we're going to talk about bond energy, which really would give you the ability to find the delta H of any reaction, whether it be exothermic or endothermic. So what you will need, of course, is a table of bond energies. This is the one from the OpenStax book. Watch out, it's on 2 separate pages, and watch out, it's flammable, as you could see earlier. And let's talk about this. What do you do when someone says, what's the delta H of something that's not in this table? Like, for example, we're going to calculate the combustion enthalpy of isopropyl alcohol, and it's not in there, right? Because this table is only so big and has only so many. The OpenStax book has a lot of different compounds, but only has so many compounds. So here's how we're going to look at enthalpy and endothermic and exothermic from here on out today. Basically, now I use that in quotes, basically, if you take a carbon-carbon bond or a hydrogen-hydrogen, maybe that's not a good example, or a carbon-oxygen bond, or it doesn't matter really what molecule that occurs in. Okay, it does a little bit. Like if you were to put next to this carbon-carbon bond a fluorine or something that's like an electron hog, or an oxygen, it might affect its energy to break slightly. But if we kind of ignore that little bit of noise, it takes about 345 kilojoules of energy to break a bond, and you release 345 kilojoules to make a bond. So think about it. Nature wants bonds to happen, otherwise elements and atoms would just stay by themselves. So it's a favorable or exothermic process for two atoms to hook up and make a bond, and you're going to have to put some work in to atomize something and break a bond, and it doesn't really quite matter that much what molecule you find it in. So if you know what molecules are, what bonds are in the molecule, you can estimate from a table of bond energies what the whole delta H of the reaction is. So just to repeat here, if I'm going to take a carbon-carbon bond and split it into 2 separate atoms, I'm going to have to put in 345 kilojoules for every Avogadro's number of bonds. And likewise, the opposite, if I take 2 carbons and they make a carbon-carbon bond, now that doesn't complete the whole octet rule, but it helps it get there, right? The octet rule wants everything to have 8 electrons, and individual atoms most of the time don't obey that. Then that's going to be favorable, and you're going to get a profit of 345 kilojoules. So now the reason I say this is this makes some of the math simpler. If you just think about it, okay, putting work into something energy-wise is endothermic, that's positive, and getting energy out of something is exothermic. Then I don't like the way a lot of textbooks present this topic because they have subtract this from that. And when you subtract stuff, folks, you can get it backwards because it matters what order you subtract something when you subtract things. So just remember this positive negative thing. Breaking bonds is positive, making bonds is negative. So okay, here we go. Now it's time for an example problem, and this is going to be our first example problem. We're going to take, I said isopropyl alcohol earlier, my bad. In one incarnation of this video, I was thinking of doing isopropyl alcohol, but I just wanted to take something that's not in the delta H of formation table, like that. That's butane. And my delta H of formation table in the OpenStax text goes up to propane with 3 carbons, and then that's it. So what do? Do you just give up on life and we can't find out what the enthalpy of that combustion is? No. We can use bond energies, because if I take the Lewis structure, which you are really well versed at now, you take the Lewis structure of butane, you see all those bonds in there, and you take the Lewis structure of elemental oxygen, which has a double bond, and it makes CO2 and water. And the way we're going to deal with this is we're going to estimate that all the bonds in the reactants are broken. We're going to add them all up, and that sum is going to be positive. And all the bonds in the reactants are formed, and that's going to be negative. Now remember, I like to take and remember that all the products are negative and all the reactants are positive. That's way easier than subtracting, because you just got done in thermodynamics remembering that, hey, delta H is final minus initial. It's products minus reactants, right? Yes, when you use the delta H of formation tables, this would actually be backwards though, because all of the bond energies are positive. So now it's flipped around. We're telling you to flip it around. So don't worry about what to subtract from what. Just remember that the products bonds are always negative, the reactants bonds are always positive, and you just slap those two numbers together and add them, and you'll get the right result that way. So okay, I've gone and written this over again. Okay, now you know what? I had to balance it, and there's a 13/2 in there. Now if that bothers you, go ahead and multiply everything by 2, but I thought that I would have less chance to make an error if I just kept it as small with coefficients as possible. So what I'm going to do now is I'm going to make a chart that says bonds broken, bonds form. This is the reactants. So I'm going to count up bonds, and then I'm going to look them up in my bond energy table. So let's first talk about what bonds there are. I see 1, 2, 3 carbon-carbon bonds. That's going to be 3 times, okay, now watch out. There's different kinds of carbon-carbon bonds. Let's look at our chart here. All right, there's a carbon-carbon single bond, which we opened up the video with. There's a carbon-carbon double bond, triple bond. We want the single bond. So that's going to be 3 times 345. I'm going to leave the units off for now, but it's all kilojoules per mole. And now what else do we got? We got a whole bunch of CH bonds. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10 CH bonds. And that's going to be 10 times some number I pull off the chart here, which is going to be, hey, CH bonds, where you at? Why am I guarantee you I'm looking right at it. Oh, it's up here on the top. I was looking down by carbon. These are all, they start with hydrogen. So that would be 10 times 415. Cool, cool, cool. 415. And don't forget this guy. Uh-oh. Can I have a fraction of a bond? Well, you know what? I'm going to do that. If that bothers you, it's okay. 13/2 of an OO bond. Remember, you could just multiply everything by 2 and you'd get the right answer. So, okay, you got to watch out. There are 2 kinds of oxygen-oxygen bonds. The one that's in diatomic oxygen is a double bond. This would be if you had something like oxygen containing compound, and that one's rare. So I'm going to take 13/2 and I'm going to multiply that by 498. Okay, and actually I'm going off my page here, so let's just add those up. And so 345 times 3 is 1035. Remember, these are all positive. 415 times, well, I could do that in my head, but thanks to crippling self-doubt, I'll do it with my calculator. 4,150. 498 times 13 divided by 2 is 3237. Add them all up. 150 plus 1035. That is positive 422 kilojoules. Keep that on the back burner. That's positive. Let's go count bonds in the products. I'll draw a little line here. My spacing on my chart wasn't all that perfect, but okay, now watch out. Each carbon dioxide has 2 C double bond O's, so that's 4 of CO2 times 2 for each. This is 8 times a C double bond O. Watch out here. This is a 5 in front of the water molecules, but each has 2 OHs, so this is 10 OH bonds. Okay, whoopsie. Drop my pen. So, gotta look them all up. What's a C double bond O? Is 741. Okay, now if you forget to do the negative at the end, do it now. I'm going to go ahead and do it at the end. Because I'll tell you what, you also have your brain can keep you in check with this. You can check yourself before you wreck yourself. By the way, this is 464 right there. 464. And I'll tell you what the check is going to be in just a little bit. All right, so okay, 741, and I'm double checking here. 741 times 8 is 5928. I'm going to do the negative now. Minus 5928. 464 times 10 is minus 4640. And I'm going to add those up. It's going to be negative 10,568 kilojoules. Now, I add those together. Don't have to worry about subtracting what from what. Delta H is the sum of those. Minus 2,146 kilojoules. Actually, it's kilojoules per mole because there's 1 mole of butane. That's why I didn't use a coefficient of 2, because then you'd have to divide that. If they wanted the kilojoules per mole, so you could compare it to a delta H formation table, you'd want to make sure you divided that by 2, but I didn't do that. Now, why am I feeling good about myself? Well, that doesn't happen all that often, but I do right now, because I know that butane's combustion should be negative. So if you did forget that negative sign, you'd add them together and you'd say, what? You mean when I take a cigarette lighter? Well, actually they're not cigarette lighters now, they're candle lighters, because cigarettes can only be consumed in like 1 square foot of the whole state. But you could say, hey, when I take my candle lighter, that's butane in there. That should be negative. What? See, and so you could keep yourself in check with your signs, because in this case, you probably would recognize that that's combustion is exothermic. Okay, hey folks, let's do another example problem and then we'll get you out of here. Okay, here is example problem number 2, and you're probably looking at this like, oh man, look at all those bonds. Well, you know, actually this one's going to be easier than it looks, and this is one of the reasons why I like the method of not subtracting but just inverting the sign of the products and the bonds in the products. This is a process, by the way, called hydrogenation. If you take something that is unsaturated and you hydrogenate it, go look at a jar of peanut butter. You'll see there's hydrogenated whatever oil in there. But what I'm going to do is the same process as the last example. I'm going to add up bonds. Now be careful, there's a different carbon-carbon bond here, but there's 1, 2, 3 carbon-carbon single bonds. So let's say 3 times C. There's 1 carbon-carbon double bond. There's a whole bunch of carbon hydrogen bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 CH bonds. Don't forget this guy. 1 H bond. That's everything on the left side of the arrow. Oh my goodness, I did not show you what I was doing. So there's all my bonds in the reactants. Now, what I'm going to do, I'm not going to dig up the numbers yet, folks, and I'll tell you why. The reason why is, well, I'm not going to tell you why yet, because it's a surprise. 1, 2, 3, 4. 4 carbon-carbon bonds. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbon hydrogen bonds. And then that's it. That's all the bonds. But look what happens. Because we've inverted the sign, or we know that the bonds formed in the products are negative, I'm not going to do all that extra work, because what's going to happen is these 10 guys will be the same quantity as 10 of these, but they'll be opposite signs. Completely cancel 10 of those. That'll be a 2 now. See what I did there? And you know, you could look up every single number and crunch it, but I ain't going to do any more work than I had to. I ain't looking up any of that. It's going to go to nothing, because 3 of these are going to be the opposite sign as 3 of these, and that's going to be a 1 now. Now all I got to do is look up, instead of 6 numbers, I've got to look up 4 numbers, and 3 of those numbers I don't have to do any mathematical operation on. So carbon-carbon double bond is 6, 11. I'm going to put the positive in there so I don't forget it. That's the real risk of this, is forgetting that the left side of the arrow is positive and that the right side is negative. And now hydrogenation you might not be familiar with. You'd be like, ooh, is that positive or negative? Is it exothermic? Okay, so you don't have a safeguard like here, like you did with combustion. Hydrogen, positive 436. Let's add those together. So 611 plus 436 is positive 1047 kilojoules. What's this? Okay, I'm put the negative in there so I don't forget. Okay, 1 carbon-carbon bond, just from last time, is 345, but negative. A carbon-hydrogen bond is 436, but I'm going to multiply that by 2. So 2 times 436, and then make it negative. 436 times 2 is negative 872. Let's add all those up. Minus 1217 kilojoules. Slap those two numbers together, add them together, and the sum of that is going to be exothermic to the tune of minus 170 kilojoules per mole. And you won't find either of those compounds in the delta HF table. And so, and you know what's funny? What if I just had that be 1 carbon more, 2 carbons more? You'd get the same number. It's kind of weird. And that's because when we are assuming, we're approaching this like with the model that all the products are, all the reactant bonds are being broken and all the product bonds are being formed, but that's not what really happens in every reaction. In the last example, it's what happened because you see nothing canceled. But the reason stuff canceled here, gang, is because these bonds here are the same before and after. What happened is that double bond broke, opened up and allowed the H's to bond to it, and so only some of the bonds are being broken and formed. And that's how lots of things work with molecular compounds. You don't have every single bond being broken and every single bond being formed, and that's when these cancel. I like this method of flipping the sign of the products and adding them together better for that reason too. If you did this where you subtract them, you wouldn't know that they would cancel necessarily as easily as if one's a different sign as the other and the exact same number. You didn't have to cancel. You could have just gone through. If you really have a lot of spare time on your hands, you could have done this whole thing looking up those 3 bonds and those 4 bonds, you know, and doing it the other way without the shortcut. But I like shortcuts. Speaking of which, I better stop talking, and that will be a shortcut for your life instead of me telling you something trivial like that peanut butter has hydrogenated whatever oil in it. Don't even look at Crisco. Ugh. Yeah, I mean, hydrogenation city. So much for the shortcut. You'll never get those 15 seconds back. I'm going to stop talking now, and we'll see you in the next video. Toodaloo!